Hello friends, I welcome you to my second lecture on similar integral equations. So here we shall consider the general form of the Abell similar integral equation. The general form of the Abell similar integral equation is given by f(x) equal to integral a to x by t dt over hx minus ht to the power alpha, and where alpha lies between 0 and 1. In the previous lecture we had considered the Abell integral equation to be f(x) equal to integral 0 to x by t dt over x minus t raised to the power alpha. So here this is the general form where ht is a strictly monotonically increasing and differentiable function in the open interval ab, and that h prime t is not equal to 0 in the open interval ab. So when you take ht equal to t here, then ht is strictly monotonically increasing and also differentiable, and h prime t is equal to 1. So all the conditions here are satisfied. So when you take ht equal to t, this form reduces to the Abell similar integral equation, and therefore we call it as the general form of the Abell similar integral equation. So we shall see how we can solve this general form of the Abell similar integral equation. What we do is, to solve the above equation, let us consider this integral a to x h prime u fu du over hx minus hu to the power 1 minus alpha, and substitute for fu from the equation 2. So in this integral the value of fu is then substituted. So integral a to x h prime u into fu du divided by hx minus hu raised to the power 1 minus alpha will become the value of fu will be integral a to x by t dt divided by hx minus hu minus ht raised to the power alpha du. So let us substitute the value of fu from the given integral equation in this integral a to x h prime u fu du by hx minus hu to the power 1 minus alpha. Then we get this integral. The limits of integration for u are from u equal to a to u equal to x h prime u over hx minus hu raised to power 1 minus alpha, and the integration limits for t are t equal to a to t equal to here it should be u, because we have replaced by x by u. So t varies from a to u and then by t over hu minus ht raised to power alpha dt du. Now let us change the order of integration here. So what we will do, a is less than or equal to t less than or equal to u, a t is equal to a here, and then u varies from a and u goes up to x. So u equal to a here and u equal to x here. So what we have, t varies from a to t equal to u. T varies from, on this line t is equal to a, so t varies from a to on this line t varies from a to u, okay, and u varies from a to x. So I think this is the figure. So this is, we have this region. Now let us take a vertical strip here. So, when I take a vertical strip, then for the vertical strip u will vary from t to u equal to x. So, now u varies from t to x, and t varies from because t is a here. So, t varies from a to, and here it is x. So, a to x, and then what we have is this integral where t varies from a to x by t, u varies from t to x. So, h prime u du divided by hx minus hu to the power 1 minus alpha hu minus ht to the power alpha dt. So, this is the correct figure where t we are taking on the horizontal axis, u on the vertical axis, and the region shaded is the region over which we are integrating. So, let us now take I to be equal to integral u to t, u equal to t to u equal to x, h prime u du over hx minus hu to the power 1 minus alpha hu minus ht to the power alpha, and then let us put hx minus hu over hx minus ht equal to s. Then from this substitution what we will get, hu will be equal to hx minus ht into s, so that h prime u du is equal to minus hx minus ht into ds. Now, by making this substitution what we will get is I will become I is equal to u equal to t to u equal to x, and then we have h prime u du divided by hx minus hu to the power 1 minus alpha and hu minus ht to the power alpha. Now, let us make the substitution hx minus hu divided by hx minus ht equal to s, so that h prime u du is equal to minus hx minus ht into ds. Now, with this substitution I becomes I equal to when u is equal to t. So, we will have hx minus ht divided by hx minus ht. So, lower limit will be 1, and when u becomes equal to x, hx minus hx will give you 0. Then h prime u du is minus hx minus ht ds divided by hx minus hu is s to the power 1 minus alpha hx minus ht to the power 1 minus alpha, and hu is equal to hx minus ht into s. So, hu minus ht will become hx minus ht into 1 minus s. So, we will have hx minus ht into 1 minus s raised to the power alpha. What will happen is then this will be equal to so I will be equal to integral 0 to 1. Now, hx minus ht to the power 1 minus alpha and hx minus ht to the power alpha will cancel with hx minus ht, and we shall have ds divided by s to the power 1 minus alpha and 1 minus s to the power alpha, which can be written as 0 to 1 s to the power alpha minus 1 1 minus s to the power minus alpha, which is nothing but integral 0 to 1 s to the power alpha minus 1 minus s to the power 1 minus alpha minus 1 ds. So, we get it as beta function alpha 1 minus alpha, and this is gamma alpha gamma 1 minus alpha divided by gamma 1. Gamma 1 is equal to 1, so it is gamma alpha gamma 1 minus alpha, but 0 is less than alpha less than 1, so this is sin alpha pi divided by pi. So, we get the value of I as pi over sin alpha pi. This is pi over sin alpha pi, and so thus we have this integral a to x h prime u f u du over h x minus h u to the power 1 minus alpha s integral over t equal to a to t equal to x by t pi over sin alpha pi dt. So, integral over a to x by t dt is equal to sin alpha pi over pi integral a to x h prime u f u du over h x minus h u to the power 1 minus alpha. Now, we will differentiate both sides with respect to x by the Leibniz rule, and when we differentiate the integral over a to x by t dt with respect to x by the Leibniz rule, then we get by x here. So, by x equal to sin alpha pi over pi d over dx of the integral a to x h prime u f u du over h x minus h u to the power 1 minus alpha. We do not apply the Leibniz rule inside the integral here, because it will lead us to the divergent integral. So, by t is equal to in replacing x by t, we get by t equal to sin alpha pi over pi d over dt of integral a to t h prime u f u du over h t minus h u to the power 1 minus alpha. Now, let us take an example on this. Similarly, the integral equation. Now, there is another integral general Cauchy general form of the Cauchy integral equation, where we have f x equal to the lower limit is a variable. In the previous case, upper limit was a variable, lower limit was a constant. Here, upper limit is a constant, lower limit is a variable. So, f x equal to x to v by t dt over h t minus h x to the power alpha, 0 less than alpha less than 1. So, here again a is less than x less than b, and h t is monotonically increasing function, and h prime t is positive. So, this has the solution by t equal to minus sin alpha pi over pi d over dt integral t to b h prime u f u d over h u minus h t to the power 1 minus alpha. This solution we can arrive at by simply following the steps of the solution of the previous general form. So, let us take an example on this. So, let us consider f x equal to integral a to x by t dt over cos t minus cos x to the power half. So, here f x is the given function, by t is the unknown function. So, when you compare it with the general form of the Cauchy integral equation, Abell integral equation, then what we get is alpha is equal to half, and h x equal to cos x. So, this will be h t equal to cos t, and alpha is equal to half. Now, not cos t, we will write it as, because we have to consider the function h t in such a way that h t is monotonically increasing and its derivative is positive. So, let us write it like this. So, by t dt equal to by t dt upon 1 minus cos x minus 1 minus cos t raised to the power half. Then when we compare it with the given general form of the Abel integral equation, alpha is equal to half and ht is equal to 1 minus cos t. So we get here h prime t equal to sin t. Now the interval given is 0 pi, where a v lie, x lies between 0 a and b. Okay, so what we have here in the, this is sin t, and we know that sin t is positive in 0 pi interval. So ht is monotonically increasing because h prime t is positive, and h prime t is equal to sin t, which is positive in the 0 pi interval. So so the solution of this Abel integral equation will be given by t equal to sin alpha pi over pi d over dt of integral a to t h prime u. H prime u will be equal to sin u into fu du divided by ht minus hu. So 1 minus cos t minus 1 minus cos u. So that is equal to sin alpha pi over pi d over dt integral a to t sin u fu du divided by cos u, and this is power 1 minus alpha here. So 1 minus half. So we have cos u minus cos t raised to the power half. So this is the solution of the given integral equation fx equal to integral a to x by t dt over cos t minus cos x raised to the power half by t equal to 1 over pi. This is alpha is pi by 2 here, alpha is 1 by 2, so sin pi by 2 over pi we have. So sin pi by 2 is 1, so we have by t equal to 1 over pi d over dt integral a to t fu sin u du over under root cos u minus cos t. So let us consider another example on the general form of the Abel integral equation. Here we have the lower limit as a variable x and the upper limit is a constant. So fx is integral over x to b by t dt over t square minus x square to the power alpha. Alpha is lying between 0 and 1, and 0 is less than or equal to a, less than x, less than b. Now when we compare it with the general form of the Abel integral equation, we have fx equal to x to b by t dt over ht minus hx to the power alpha. So ht is equal to t square here. So ht equal to t square is strictly monotonically increasing function in AB because h prime t is equal to 2t, and so over the interval AB, open interval AB, because A is could be 0 also. So in the open interval AB it is strictly positive. And therefore we can find its general solution. We can find the solution of this integral equation. The solution of this integral equation let us find by the formula this one. So by t is equal to minus sin alpha pi over pi d over dt integral t to b h prime u d f u du divided by hu minus ht raised to the power 1 minus alpha. So, this is minus sin alpha pi divided by pi d over dt integral over t to b h prime u is 2u. So, 2u f u du divided by u square minus t square raised to the power 1 minus alpha. So, we get the solution of the integral equation as by t equal to minus 2 sin alpha pi over pi d over dt integral t to b u f u du over u square minus t square raised to the power 1 minus alpha. With that, I would like to conclude my lecture. In the next lecture, we shall discuss the Cauchy integral equations. Thank you very much for your attention.